Okay, so hello again everyone. In this video we're going to be looking at benzene. This is going to be the first of two videos. First is going to be looking at the structure of benzene, and then the second will be looking at some of the things you can do with benzene, so the reactions of benzene. So benzene is a very interesting molecule. It's a very famous molecule. It has the chemical formula C6H6. So if you try and think, right, how on earth am I going to draw a chemical with 6 carbons and 6 hydrogens, it's going to be quite difficult. So we'll have a look at how you draw that in a little bit. It's a colourless liquid. So it's a liquid at room temperature and it's colourless. It has a distinct smell. So it has quite an obvious smell to it. As do quite a lot of organic compounds, but it has a distinct smell. And most importantly of all, it's the parent molecule. So it's the parent molecule of lots of important chemicals on the planet. So of lots of important chemicals. So most drugs that you'll come across, that you take, have got a benzene sort of structure as their root. So if you googled what the structure of paracetamol is, which I'm sure many of you or most of you have taken, benzene will be part of that structure. If you look at what ibuprofen looks like, benzene will be part of that structure. If you take some other drugs for other reasons, more than likely benzene is going to be part of the structure of those drug molecules. So not just drugs, but drugs are the example I've picked as a parent molecule of lots of important different chemicals. So what on earth does it actually look like? So there's a little bit of history that goes with benzene. The first person to sort of discover benzene and try and suggest a structure for benzene was a guy called, as a scientist called the surname Kekulé, so it's called the Kekulé structure of benzene. So he was the first person to sort of suggest a structure for benzene in about 1825. So what he did was he thought, right, that's the chemical formula, what can I do to make, how can I make a molecule fit that chemical formula? So what he decided was benzene was a cyclic molecule that looked like this. So there's my 6 carbons. He said every one of the carbons can have 1 hydrogen, like that, and then there would be a double bond on every other carbon. So if you count each of those carbons now, the bonds in each of those carbons, they've all got 4 bonds. So that sort of fits the chemistry that we've studied to date. So that was the first sort of suggested structure for benzene in about the 1800s. If you were to draw the skeletal formula for that, it would look a little bit like this. Okay, so that's the skeletal formula for the Kekulé structure. Now, this was the first structure that was suggested, and I'm sure you can see this coming. There are problems with this structure. So there's 3 main problems with the structure. And as time went by, people discovered these problems with the Kekulé structure for benzene. So the first problem is to do with the reactivity. So I'm going to call it the reactivity problem. And this is problem number 1, so let's just call it problem number 1. So problem number 1 is the reactivity problem. So what's wrong with this structure in terms of reactivity? Well, if you look at it, it's got alkenes in it. So you'd expect this benzene ring to react in a similar way to an alkene. So let's think of a reaction of alkenes. Here's ethene. If I added bromine to ethene, like this, bromine would add to the double bond, so we'd get this as a product. So the double bond's lost, and this is an addition reaction of an alkene, which you will have studied in year 12. Now if I try and do that with the benzene ring, so if I try and add bromine to benzene, nothing happens, so there's no reaction that happens. So this is our problem now. We've got something with 3 alkenes in it, so we'd expect it to react very happily with bromine, but it doesn't actually do the reactions we're hoping that it does. So this would go from orange to colourless, whereas this one over here would stay orange because the bromine doesn't react. So that's the first problem with the Kekulé structure. The second problem with the Kekulé structure is the shape and the bond lengths. So I'm going to call it the bond length and shape problem. Very creative naming. Bond length and shape problem. So, what is the bond length and shape problem? Well, a carbon-to-carbon double bond in a molecule has a particular length. So the length of a carbon-to-carbon double bond, not that you need to know this, but I think it's helpful for context, is 0.134 nanometers long. So that's how long these 3 bonds should be. And a carbon-to-carbon single bond is 0.153 nanometers long. So this bond should be slightly longer, and then these 3 bonds should be slightly shorter. So actually, although we draw it as a hexagon like this, the Kekulé structure shouldn't be a perfect hexagon. Now, as technology advanced beyond Kekulé's time, there's something called X-ray crystallography, which is able to basically X-ray the molecule and look to see what sort of shape it is and how long the bonds are. And what they found when they looked and studied the structure of this molecule in more detail was that all of these bonds, so this bond here, this bond here, this bond here, this one, and this one, were all the same length. So actually all of the bonds, all of the carbon-to-carbon bonds, were 0.139 nanometers long. So you can see this bond length is somewhere in between a carbon-to-carbon double bond and a carbon-to-carbon single bond. So there's another problem with the Kekulé structure, is the bond length problem of the carbon-to-carbon bonds, and then as a consequence of that, a shape problem. Because all the bonds are the same size, benzene was found to be a perfect hexagon, whereas Kekulé would say, because these bonds are different size, so these bonds, it's not a perfect hexagon, it was found that actually it is a perfect hexagon. So that's the second problem. And then the third and final problem is the stability problem. So what is the stability problem? So this one's slightly more awkward to explain, so I'm going to show you the background to how they discovered this problem. So this reaction here, when I do it and I make cyclohexane, so I'm adding to a single double bond, the energy change, so delta H for this reaction is minus 100. Delta H is minus 120 kilojoules per mole. So this reaction here, minus 120. If I have 2 double bonds, so there's my 2 double bonds, awfully drawn benzene, but there we go. So 2 double bonds, I'm adding 2 hydrogens, and I again make cyclohexane out of it. The energy change is minus 240 kilojoules per mole. So we would expect then, when we add the third double bond, so 3 hydrogens, we would expect this reaction, hopefully you can see the pattern, 1 double bond, minus 120, 2 double bonds, minus 240. We would expect the energy change for this reaction to be minus 360 kilojoules per mole. So that's the expected energy change. But actually, when we perform this reaction, the energy change ends up being minus 208 kilojoules per mole. Now, what that shows us is that this reactant here is much more stable than we were giving it credit for. So let's just recap what we've learned so far then. So benzene, chemical formula C6H6. Kekulé, a scientist called Kekulé was the first person to suggest the structure. This is the structure he suggested, so alternating single and double bonds between the carbons in a cyclic structure. And then as time went by and scientists' technology advanced and things like that, problems were discovered with this. The first one was the reactivity problem, so the fact that benzene doesn't react like alkenes, even though it's, according to Kekulé, it's got these 3 double bonds. It doesn't react like alkenes. Second problem is the bond length. So you'd expect benzene, when you looked at the structure of it and studied it, it would have carbon to carbon double bond lengths, that length, and single bond lengths, that length. But actually, when they looked at the structure, it was found that these were the bond lengths, so they're all the same size, so it's a perfect hexagon. And then the final problem is the stability problem, which we would expect, this is the best way to show it, when we perform hydrogenation reaction with benzene, we'd expect an energy change of minus 360 kilojoules per mole, but actually it's far more stable with minus 208. So it's far more stable than we give it credit for. So the question is now, if that's all the problems with the Kekulé model, how can we make a model that solves those problems, that actually shows what the structure of benzene actually is? And this is where today's model comes in, which is called the delocalized model for benzene. So delocalized model for benzene. In this model, we assume that each of the carbons is joined in a ring to the other carbons. All these bond lengths are the same length. They're all joined to one other hydrogen. So there's all the atoms accounted for. We've made the bond lengths the same, but we've still got to make sure that all the electrons have been used. So what happens in the delocalized model for benzene is, let me get another pen, the carbon atoms will have p orbitals in this orientation. So every single one of the carbon atoms has got a p orbital in this sort of direction. So here's my p orbitals. So carbon has got one electron. There's one electron in each of these p orbitals, just floating around freely between it. And what happens is you get the sideways overlap of p orbitals. So sideways overlap of p orbitals, and what that will produce is we keep our carbon ring like this with our hydrogens, but it will produce a delocalized ring of electrons. So there's going to be a ring of electrons above the ring and a delocalized ring of electrons below the benzene ring as well. So these two rings are delocalized pi electrons. And what that does then is it stabilizes the benzene ring even further, and that then accounts for this extra stability that we saw. There was a problem in the Kekule structure. So this benzene ring now is far more stable than the Kekule structure would have predicted. So how do we draw that in shorthand? You do need to know how to explain this chemistry, but how do we draw it? What's the short way of drawing it? So this is how we drew the Kekule structure, which is incorrect, so don't draw benzene like that. This is how we need to draw benzene. Okay, so that little circle in the middle is representing these delocalized pi electrons. So let's just recap. The reason this model is better than the Kekule model is in this model all of the carbon-to-carbon bonds are the same length. It's a perfect hexagon. It accounts for the extra stability of benzene. So these delocalized pi electrons stabilize the benzene ring, which account for that extra stability. And then that extra stability also starts to explain why it is unwilling to undergo those reactions that alkenes undergo, because we haven't got these double bonds, these concentrated areas of electron density. Benzene doesn't really undergo those addition reactions that alkenes would undergo. Okay, so the only other thing I think that might be worthwhile doing is, I think this sort of model is sometimes a bit hard to picture, especially maybe with my drawing. So if I show you this image, which I've taken off the internet, let me just sort out the brightness. That looks a bit happier. So you got the hexagon ring here, all the carbons are the same length, and then because each of the carbons, if you look at the black lines, they're all forming 3 bonds, which means there's one spare electron. So the spare electron is in this p orbital, which is above and below the benzene ring. So we say it's above and below the plane of the benzene ring. And what happens is each of these orbitals overlap. So this orbital here is going to overlap with this orbital and this one here, and they're going to do it in a form sort of like a ring formation, and then the one from each of the carbons becomes part of that ring formation, and they're free to move wherever they want. So they form a delocalized ring, delocalized pi ring of electron density, which is above and below the plane. So I think that's a really nice drawing actually to show those free moving electrons which are above and below the plane of the benzene ring. So benzene doesn't undergo addition reactions because those rings, these delocalized electrons, are far more stable than they would be if they were concentrated in between the carbons. So in the next video we'll look a little bit about what reactions can we do with benzene if it doesn't undergo addition reactions. But that's the structure of benzene anyway.